circular motion. Objectives: to understand the concept of uniform circular motion, to obtain an expression for the acceleration of a particle performing uniform circular motion. What is uniform circular motion? Uniform circular motion. Definition: when a particle moves in a circular path such that its radius vector makes equal angular displacement in equal intervals of time, then the particle is said to be in uniform circular motion. Or when a particle moves on the circumference of a circle with uniform angular velocity or constant linear speed, then it is said to be in uniform circular motion. See these illustrations. When the moon is revolving round the earth in a circular path, its motion is in uniform circular motion. A satellite revolving round the earth in a circular orbit performs uniform circular motion. These are the examples of uniform circular motion. In uniform circular motion, magnitude of linear velocity speed, kinetic energy, angular velocity, and angular momentum with respect to the center of circle remains constant, but velocity changes due to change in direction. In uniform circular motion, all real vectors like velocity, acceleration, force, momentum are constant in magnitude but continuously change in their direction. In uniform circular motion, the angular velocity is constant and angular acceleration of the particle is zero. A particle moving with constant speed in a circle is not in equilibrium, as net force is there, which is acting as centripetal force. Now we discuss about centripetal acceleration. Centripetal acceleration. When a particle moves in a circular path with uniform speed, the direction of velocity changes at every point on the circumference of the circle continuously, but the magnitude of the velocity remains constant. The change in the direction of velocity implies that there is some acceleration. This acceleration is called centripetal acceleration. It directed towards the center. Now, obtain an expression for the acceleration of a particle performing uniform circular motion. Derivation. Consider a particle P moving on the circumference of a circle of radius r with constant angular velocity omega. At any instant of time t, let its position vector r bar be denoted by OP bar. Taking its initial position along x-axis, it rotates through an angle theta is equal to omega t in a time interval t. Resolving r bar into x and y components, we get x component of r bar as r cos omega t into I, and y component of r as r sin omega t into j. Therefore, r is equal to r cos omega t into I plus r sin omega t into j. R is equal to r into cos omega t into I plus sin omega t into j. Equation 1. To get the linear velocity of the particle, the above expression is to be differentiated with respect to time. V is equal to dr bar by dt, that is equal to r omega into minus sin omega t into I plus cos omega t into j. Equation 2. From the above equation, we observe that the velocity of the particle changes with time, so it will have linear acceleration. Its linear acceleration can be obtained by differentiating the expression of the velocity of the particle with respect to time. A is equal to dv by dt, that is equal to r omega square into minus cos omega t into I minus sine omega t into j. That is equal to r omega square into minus of cos omega t into I plus sine omega t into j. The magnitude of the linear acceleration is r omega square. The direction of the acceleration is given by minus cos omega t into I plus sine omega t into j, which is opposite to the direction of r. That is, the linear acceleration is directed along the radius towards the center. So, it is called centripetal acceleration. Since it acts along the radius and normal to velocity, it is also called radial acceleration. Magnitude of centripetal acceleration AC is equal to r omega square, that is equal to v omega is equal to v square by r.